Hey everybody, today we'll be doing another quick video, and today I will be doing the hexadecimal counting system. And after we introduce the hexadecimal, we will do some conversion. We'll do two examples and going from binary to hex. So let's say we mentioned last time that the binary is base 2, right? We say that the decimal was base 10, the binary was base 2, and now we introduce this counting system that this is base 16. This is base 16. So we have to actually count on base 16 now. And this is important because as you can see, if you have a lot of numbers, for example this one, how can you represent that? If you had a bunch of numbers like this, it's going to get messy, to actually translate. So it's easy to actually put some numbers and letters to represent that number. Alright. So we will go through that, but the computers use the hexadecimal system to allocate an address in memory. Or maybe a microcontroller has some certain address that it will kind of point to that address when the microcontroller is performing a function. It's a lot of and then the address is usually given in a hexadecimal form. Okay, so the hexadecimal basically help to reduce the amount of numbers, because like I say, F can be 15 can represent by F and all these numbers. So we count last time that we say that in the decimal system and also in the binary, after the 10 start counting by letters. So 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. Now, this table you can actually learn how to derive it, or maybe you can memorize it. We can memorize it, right? So it's helpful to kind of have this, be familiar with this table, and also this the hexadecimal system from 0 to F. So let's see if we can actually do these two problems that we have here, right? So we say that it's the hexadecimal is base 16, right? So when we write the answer at the end, it's going to have like a little 16 like that in the bottom. Like this one is base 2, so usually put 2 on it. Like I say, some books put the 2 on it. Other books, they don't, but it's helpful to have the 2 on it. The 2 for the base 2, and also on the base 16. It's also a good idea to have that 16 in there, the base, the 16 to represent the base 16 like that in the subscript, right? In a kind of subscript form like that. Okay, so let's do these two problems here. So in A, actually what I usually do, and this problem kind of helped me out, is that I start from right to left and I start counting by bits. And I usually use in problems like this, we use here a 4-bit table, so I have 4 bits, right, all the way up to 16. So basically we can actually use 4 bits here, right? So let's see. So we go from right to left and count 4, and that would be the first 4 bits. And then here count to 4, and that will be the next 4 bits, right? And here next 4 bits, and from here to here another 4 bits. Now notice that I can use the table for that, right? And I can actually find the numbers. See? I got one of them, which is this, right? Or if you don't actually how the table, you don't have the copy of this table, you cannot remember, what you can actually do is start doing the math the long way, right? So in this case right here, so see that all I have to do right here is, I know that this is 1, right, times 2 to the 0 power, right? And then I put a plus sign because I'm going this way, right? And then I put 2. So I put 1 times 2. Let me just make that a little more clear. So 1 times 2 to the first power, and then plus, and then I can say that plus, right? And then I said 1 times 2 to the 1 times 2 to the second power, right? And then the next one I don't have to do it because it's 0, right? That makes sense. Now look here. In this case right here, I get 1. The first one I get 1. The second, and I put a plus sign in there, and I put a 2 in there. And then the third number, which is this one right here, I get 4. See? Plus 4, right? It's kind of hard to see. But if I do it right here, let me just do it right here so you can actually see it. Let me do it in this space right here, right? So in the first one, you want to do it the long way, or you can use a table, right? But let's say you don't have the table with you, right? So here you do let's do 0 times 2, that is the 0, 1, 2, 3, so the third power, right? But that is plus 0, so it doesn't matter. So, and then I do 1 times 2 squared plus 1 times 2 to the 1 power plus 1 times 2 to the 0 power. See that? Okay, so do the math. Here is 0, right? But here you got a 1, here you got 2, and here you got 4, right? And here you got a 0, right? Okay, so here is 4. Okay, so now isn't that 7? 4 plus 2 plus 1 is equal to 7, right? So that is equal to 7. And that is equal to 7 here. So actually that will be 7 right there, right? Now let's do the next one. Here you got 1, here you got 2, but this is, this is to the 1 power, but it's 0, right? And here on the 2, actually, here on the, okay, this is 0, 1, 2. So on the power of 2, so you got a 1. You got a 1 times 2 to the power of 2, right? So that's 4. So then that will be 1, then plus 4, right? I didn't write a 0 because it's not necessary, right? So let me just write this here, so you can actually see, right? So we know that is, and then this bit right here is 1, I'm sorry, it was 4 plus 1, and this bit right here we said that was 4 plus 2 plus 1, right? So here is, we know that this is 10, right? It's 1 0 1 0, that represents 10, 10, but it's actually 8, right? And then here, this is actually 12, right? That is 12, which is represented by C, right? Now, this is the kind of tricky part right here. Don't make the mistake and add the whole thing, right? Just add the bits, the 4 bits that you separated by, right? So you separated by 4 bits, add those bits and add them together. Add just the bits, the 4 bits, right? And each block. Don't add the whole thing, right? So here will be 5, right? And here will be 5, and here will be 7, right? So technically, all right. So it will be CA57. That will be the answer for that, right? So the answer for this will be CA57. Okay, so now look at the answer. Look at the answer. It looks better. I mean, it looks smaller, right? And that is the purpose of doing this. Right? That is the main purpose of doing this. So, CA57. Alright? So, that is the answer for that one. Okay? So, let's do the next part. Let's do that the next part, right? But again, like, let me say it again. See how this big number of zeros and ones, and we actually reduce it by 2 letters and 2 numbers, 2 integers, right? So it's kind of helpful to have, if you can represent this number into this number, it looks, it looks less complicated. So, okay, so now let's do this problem here, right? Now let's do this problem. And here, what I usually do when I am counting this, I see how many 4 bits blocks I get, right? And the reason why I start from right to left is because if I need a 4 bit, if I need some digit, some zeros to complete a 4-bit block, right? I can add it to the left here, but to the right is going to create problems, right? So I want to add 0 to the least significant bits, right? If I need to complete a block, right? A block of 4 bits, right? So let's do this again, right? So now let's do this block. All right, that's the first one, right? 4 bits. And then four bits, and then 4 bits. So basically, I need more digits, right? See, I only have 2. I have 1, 2, 3, 4, 4 complete 4-bit blocks, right? So I need to add more digits to the left. So what I'm going to do now is do the following. I gotta say 0, 0, 1, 1. I already added to the left here. See that? Right? Then, right? And then I do 1, 1, 1, 1. Right? And I do 0, 0, 0, 1. Right? And then I do 0, 1, 1, 0. Right? And then I do let me just, okay, and then I do 0, okay, I'm here, so, okay, never mind, it's 1, so it's 1, 0, 0, 1. Okay, so now I have the complete 1, 2, 3, 4, 5. 5 blocks, right? 5 blocks of 4 bits. Okay, so now that I have this, I actually can represent these numbers by either by the table or doing the math, right? So here, in this case, here the first bit is going to be what? It's going to be 2 times 1, right? Or 1 times 2, you can say, to the power of 0, 1, 2, 3. Power of 3 plus 0 plus zeros. I don't care about the zeros. Plus 1 times 2 to the 0 power, right? So this is 8, right? This is 8. Actually, no, hold on a second. Here, let me do this again. Don't worry about it. It's about this one. Because I am doing this now. Right? Actually, no, I was right. I was doing this. I was doing that. So I have 1 times 2 squared. 1 times 2 squared. So 1 times 2 is to the 3rd power, right? Plus 0 plus 1 times 2 to the 0 power. Okay, so this here is 1. Okay, so this is 0, this is 0, and this right here is 8. So this and this is what? Equal 9, right? And also we can actually pick it out from the table too. Like I said, if your professor let you to use the table, well, just use the table, right? So here is 9, right? So actually this one right here is 9. So you can actually write here is 9, right? Now, but again, you need to remember you're not adding the whole thing, you're adding just the 4 bits, right? So now here another number. So in this block right here, so it's going to be, in this one right here, it's going to be 0 times 2, 0 times to the third power plus plus 1 times 2 to the second power plus 1 times 2 to the 1 power, right? And plus 0, right? Doesn't matter. Plus 0 times 2 to the 0 power, right? So here, this is 0, this is 1, this is 4, this is 4, right? So now look at this. So basically what it is just 5. And we actually can pick it from, actually no. No. This is actually 2. Right? So basically that is 6, right? So this one is 6, and you go to the table, that's what it is. It's 6, right? So okay, so we're done with that, right? Now this is easy. This is just 1, right? Because 0 plus 0 plus 0 plus 1 times 2 to the 0 power is equal to 1. And this is 1, right? Or you can memorize the table, the numbers of the tables, right? There are 2. Alright, so that is that one. And then we know that this is what? This right here, this 4 digits, 1, 1, 1, 1, 1, 1, 1, 1. This is what? This is simply 15, which is in hexadecimal is F, right? Actually, you know what? Let me just write this number here, because this should be here. 9, 6, 1, F, right? Now look at this. Look at the last one right here. So here you get what? You get 3, right? Why? Because that's what it is. It's 3. But you can actually do the long way too. You can say 0 plus 2 to the third power plus 0 times 2 to the second power plus 1 times 2 to the 1 power plus 1 times 2 to the 0 power, right? So this one right here, 0 plus 0 plus 2, right? 2 times 1 to the 0 power is 2. 2 times, okay, and then 1 times 2 to the 0 power is what? It is 1, right? So then you add them together and you get what? You get 3. Okay, and that's the number in those 4 bits. Now, the final answer for this is 3 F 1 6 9. Okay, and remember that we say that we're doing what? Do we doing base 16. Alright, so base 16, and this is base 16, right? Alright, so okay, so now you see the big number in binary, and it was reduced to what? 1, 2, 3, 4, 5 different one letter and 4 numbers, right? So this is how you do binary to hexadecimal conversion, and I hope you learned something out of the video. Thank you for watching.